Hello everyone. So last classes we discussed the various applications of computational fluid dynamics, domain where CFD can be applied. As we seen, CFD useful nearly every field where fluid dynamics play an important role. This includes both the design of new systems and analyzing of existing designs. It is a powerful tool with the several advantages over traditional experimental method. So it is important to remember that CFD must always validate it against the experimental data to ensure its accuracy. Because during the CFD simulations, there are so many assumptions we considered, so that we can match with so that the softwares can work efficiently or approximately whatever the results we are getting with the help of CFD, it will be approximate results. So while validating it against the experimental data, so that we can have the accuracy of that CFD results. Only once we validate the CFD results, then only we can trust on the CFD data for further analysis or design or development of the system. So in our previous discussions, we also cover the fundamental component required for the CFD analysis. What are the process includes? So this includes pre-processing, grid generation, solver setup, post-processing. So in high quality research paper, you will often come across the detailed results in the form of diagram like what we have shown in the particular PPT. So you can see the aeroplane, and where there are so many colorful contours, blue color, orange color, yellowish color. So these are the output. Once we are applying once we apply all the conditions, once we done with the pre-processing, solver setup and all, finally we will come with this type of beautiful contours after completion of our simulation. So now, so what are the results we are getting from the simulation? Maybe qualitative results. So this refers to the visualizations such as contours or streamline that shows how flow behavior is different, how such that contours or streamline that shows how flow behaves in the different regions. On the other hand, quantitative results. So it gives us numerical data like pressure distribution along specific line, or coefficient of lift, or coefficient of drag at various locations. So for any CFD analysis to be considered reliable, both qualitative as well as quantitative results must be aligned. So we must ensure that these results are validated before applying them to new geometry or flow condition. So as I said, types of results, there may be qualitative results where we can visualize the data in terms of contour, streamline, and quantitative results in terms of numbers, so measure pressure distribution, line back coefficients and all. So there are so many common softwares generally we use for CFD analysis, ANSYS like ANSYS Fluent, OpenFOAM. So these software tools are built on different framework for solving the Zorn equations of the fluid flow. Each follows specific methodology for discretizing the conceptual or computational domain. So selecting the numerical scheme and solving the equations which governs the behavior. Some of the most common CFD software tool includes package, Drupal in C or C++, ANSYS, CFX, and other developed by companies like Altair. So while these tools differ in terms of the underlying algorithms and approaches, they all share common objectives to solve the fluid dynamics problem through numerical simulation. So what are the conditions? It may be of compressible or incompressible. Okay, whether solver is pressure based or density based, we will cover all the topics in a systematic way. But okay. Now the primary difference between CFD software package lies in how they structure the computational grid and how the equations are solved. The commercial CFD tool, what we encountered are based on the finite volume method. On the other hand, many of the research tools used for high fidelity simulations like LES, large eddy simulations, or direct numerical simulation, okay, often used for the finite difference method. So these two are the most widely used method in the CFD, and it's crucial to understand the key difference between them. So finite difference method is relatively simple when it comes to representing the differential equation using finite difference scheme. So to illustrate, let's consider the linear convection equation, which is similar to the wave equations. You might be knowing the wave equations. So this is often we call as a convection equation. This equation we generally call as a convection equation. For example, the heat equation describes diffusion, and depending on whether it is steady state or unsteady state, heat behavior is different. So steady state heat equation is typically solved elliptical equation. Steady state elliptical equation. So steady state solve elliptical equation, and unsteady solve parabolic equation. So now again consider this equation dou by dou t plus c plus dou by dou x, which is equals to 0. So typically if we say velocity, so suppose I am saying dou u by dou t plus c dou u by dou x. So this is a conventional linear equation, and these equations which we have, it may be time dependent or space dependent. As you see, dou u by dou t, which is a time dependent, which generally we call as a temporal term, which represents the rate of change with the time, and the term that depends on the flux or convections. Better term for this would be advection, which describes advection. So which describes how certain quantities are being transported or carried along with the flow. So in this case, the quantity u is transported at a speed of c. Okay. So whatever the c we are having, dou u by dou x equals to 0. So quantity u is transported at a speed of c. C is a constant. So if we change this equation into nonlinear equation, like suppose how to change into nonlinear equation, dou u by dou t plus, instead of c I am saying u, and this is again, sorry, here it is x. Okay. So this way we can turn this linear equation into nonlinear equation. Now u is being transported at the speed of u, which is unknown quantity that must be determined through the solution process. The key difference here is that c is a constant, but u is not. Okay. So u is being transported. This u is being transported at the speed of u, but u is unknown. So that's why we are saying it is non-linear equation, and this is linear equation. So to solve these equations, we need to discretize it. We will discuss earlier that we can represent the spatial domain as a grid. So represent this discretization in terms of in the simplest form. If we have grid where x is the spatial coordinator system and fx, as we seen in the first previous class, like this one. Okay. So f of x in this y direction, and this is x. So whatever the differential equation we are having, that we have represented in the particular term, right? So if we can approximate the derivative in terms of the difference between the value at the adjacent grid point. Okay, suppose this is our I, and this will be I minus 1, and this is I plus, this is I plus 1, this is I, and this is I minus 1. I minus 1, I plus 1. So this is the 1D example. If we have 2D, then what we have to do? We have to go for this way, discretization into number of elements, and suppose this is this way. So this is I plus 1, I plus 2, I plus 3 in this way along the x direction, and in the case of y direction, j j plus 1, j plus 2, j plus 3, and so on. Okay. So in this particular equation, what we have for convection term, a convection equation. So if we go for the time derivative, time space, then obviously we are saying generally time I and j will be the representation for special derivatives, special term, and for temporal time derivative term, generally we used n. So suppose I am dealing with the time steps n, n plus 1, n plus 2, or n minus 1, previous time step of n, then in that case, I can simply say if I am about to discretize the particular equation or discretize the equation, this equation, what can I do? I can go for, if it is depend on the time, then for the same point, suppose I am taking the example it again here. This is the equation. What is the equation we are having? We have the equation dou u by dou t, which is temporal derivative, plus c dou u by dou x, which is 0. Then if we want to discretize the derivative, how can we discretize? That is time, it is a time step, temporal derivative. So I can see for the particular situation, suppose I am having I, so this will be I plus 1, I plus 2, this will be I minus 1, I minus 2, and so on. And for the time that suppose I am saying n is the time step. At this point, this is I. So for the say of what is the situation at I position after time n. Okay. So this is n time, this indicating the time. N plus 1 time, n plus 2 time. So what is the situation at I position after some time, n plus 2 time, or n plus so on. So what is the situation if I want to identify, then that time I can say what is the situation after n plus 1 time at I position. Then how can I write? Ui n plus 1 minus ui n. What is the situation at nth at the current time, and what is the situation at I location after n plus 1 time. So delta t is the time interval for change in the value of u with respect to the time. Then if we go for the next space derivative, how can I write? What is the position? What is the value of u at n plus 1 position minus, suppose I am saying u at I position and n divided by delta x, that will be equals to 0. So this is a simple way we can say. So it is temporal derivative. This is our temporal derivative, and this is advection. This is advection or space derivative. Okay. This is linear term because u will be why we are saying it is linear, because the u is transported at the speed of c. U is transported at the speed of c. So this is the simple way we can have this discretization. This is finite difference method. Now for you can observe that for defining the finite difference method, there is some structure, known structure of the system. Okay, there should be the delta x constant for all the elements, right? Means if I am having this particular section, then this is delta x, this should be this also delta x, and this should be also delta x. So right, accordingly this will be delta y, this also delta y between the two nodes, and this is also delta y. So it will be same for if we defining the finite difference method. So this is the basic form of the finite difference equation for higher dimension problem like 2D. You would set up the grid in the both x and y direction as I discussed, and derivative would be calculated with respect to both coordinates. Okay, so now take the this is the simple example, but instead of having the particular square shape, suppose I am having triangular geometry, suppose this way. Okay, so in that case, how to discretize? I have to make the various shapes like this way. I have to discretize it in a number of ways. I can discretize it, but the element, each and every element may be of having a chord element or tri element. So it is very difficult for the discretization with the help of finite difference method, because every time the node difference, distance between the two nodes may be is always changing. So calculating the derivatives in both the x and y direction is difficult. So for solving such type of equations, we are approaching towards the finite volume method. So we would apply the boundary condition to the system, for instance, setting up the velocity 0 along the wall or no slip conditions, and setting up the moving lid on the top. Okay. So now suppose we want to change the cavity shape for something more complicated like triangular cavity. The equation remains the same, but the grid setups becomes stickier. So if you try to discretize with the regular grid, what we have seen for the rectangular grid or a square grid, so we will run some issues, especially at the corners where we will get singularity in the grids. You can see there is only single grid at this location. Okay, only single grid at this point at the corner. So in the grid, so it makes very difficult to solve the problem. Now one solution is to use a unstructured or non-structured grid that adopt to the regular geometry. For example, we can create triangular grid that fits the cavity shape or places finer grid point near the wall where the flow gradients are higher, allowing us to capture the velocity and boundary layer property more accurately. Okay, so finite difference method is simple approach for solving the basic differential equation, especially for one-dimensional problem. However, for more complex problem, 2D, 3D, so like triangular or other irregular domain, we need to use flexible grids, which is where the finite volume or finite element method comes into picture. So these methods allow us to handle more complex geometries and better capture the flow characteristics, especially multi-dimensional problems. So if we want to capture the boundary layer in 3D flow, okay, so we should add the prism layer instead of having this particular tri element. If in the case of 3D, we should have prism type of elements. Okay, so it means by this is we might create few layers of grid here, maybe 2 or 3 layers to capture the boundary layer effectively. Okay, and we can fill up the particular case with the different grid arrangement. So what we can say, finite difference method is simplest way to discretize the differential equation, as we seen in the conventional equation, or same thing we can apply for the convection. So dou u by dou t is a temporal term, or it has changed over the time, and c is the speed constant which we have seen, and dou by dou x special derivative depending how the quantity is converted. Okay, so finite approach is more involved but highly accurate method. So finite element method, what we have approach we have, it is more accurate but highly it is more involved. So finite element approach is more involved but highly accurate method, originally developed for structured analysis. Now it has become popular in the CFD also, with some research course utilizing this approach. The term element comes from its structure analysis origin. So in the finite element method, accuracy is achieved through P refinement or H refinement. P refinement refer to increasing the order of the polynomials with each element, which enhances the solution accuracy by better capturing the gradient. H refinement involves adjusting the size of the element, where decreasing the element size can be improved the solution precision. So together these refinements helps achieving greater accuracy in simulation. So what is the advantage of finite difference method? So it is simple to implement, especially for simple problem like conduction conversion can be used to calculate the higher order stream by incorporating the more bits, void or higher effect. But it is having some advantage. So it doesn't with the complex geometry like refoil shape, air shape, having some um, different shape. So as it requires subtle hard to apply to non-rectangular or irregular domain. So in the case of finite volume, it can be applied for the complex geometry where subtle are impractical. Instead of point-wise relative, the method involves integrating over the finite quantum volume. Okay, so this definition is the integral form. So instead of differentiating the integral form of the function. For example, of course, this is the convection equation. What we need now. Okay, so simple convection equation in the control volume system. How can we write it? We can say this is dou psi by dou t plus mu by. This is a simple way where we can define the control volume approach. So psi is the quantity being transported. Well, it may be velocity or it may be temperature. So divergence theorem is applied to convert the volume integral into surface integral. So what is the divergence theorem? We will discuss in the coming class. So finite volume can easily handle unstructured gauge in unstructured grids. In the case of 3D, it may be hexahedron, tetrahedron, okay, prism type. So in the case of 2D, it may be tria or chord element. So at each cell, fluxes are calculated based on neighbors with information from left and right cell used to determine gradient. So finite volume having some advantages. You can be handled any geometry including irregulars or complex domain. FVM finite volume method is suitable for aerospace simulation with the slat, flaps and other complicated shapes, and can be used various types of cells or hexagon or tetragon or prism type of. But it is having some limitations, limited by accuracy by comparing to finite difference method. Lower order accuracy because it only uses neighboring cell, no information about distant cells. The solution is often less accurate than structured grid finite difference approach. That is the disadvantage we are having for finite volume compared to the finite difference method. So finite element method is more accurate but more complex. Okay. So use of structured analysis and gaining finite element. Finite, now we are talking about the finite element. FDM, FVM, and this is FEM. So FEM finite element method is more accurate but more complex. So use of structure analysis gaining high accuracy in both the geometry and solution we required. So it involves subdividing the domain into usually polygon or polyhedra. So it is advantage is high accuracy can be achieved by using polynomial approximation within each element, and it is effective for highly irregular geometries. These are the types of formulations. Formulations depend on whether it is incompressible, compressible. Because incompressible, there is no change in the density, but compressible, there is always change in the density. So Popal or segregated approach determine how variables are solved together. Okay, like U, W, like that. If the combined coupled things we are solving together, then it is saying otherwise if we say U, rho, W, these are solving independently, segregated approach. Okay. So this way we can having the coupled or formation of the CFD. Then next is grid type and topology. So in the grid uh, type or topology where we don't rely on fixed grid structure, instead we use point cloud structure. Okay, which represents the fluid flow. So formation of the fluid flow problem, incompressible or versus compressible. The choice between incompressible and compressible formulation impact how the flow equations are solved. Like incompressible flow uses primitive variables like velocity and pressure, while compressible flow requires conserved variable which accounts for varying density, because the property which we are having, suppose volume, pressure, these are the function of density. So it may having conserved variable. So coupled and segregated solver where all variables like density, velocity, pressures are solved simultaneously. This approach is more computationally expensive but yield better results. So segregated solver solves the equation sequentially one after other, typically starting with the mass conservation followed by momentum, then energy equation. And pressure velocity and pressure stream function, which is pressure velocity formulation, is simpler and more commonly used, while vorticity stream function formulation is more complex and suitable for certain problem like rotational flow. And again, there is a Cartesian coordinate system and curvilinear coordinate systems. So is it Cartesian coordinate system is easier to handle mathematically and computationally, and they are often quite used in a simple geometries. But curvilinear coordinate system used for more complex geometry, they allows better alignment with the body or flow features. And there is another approach, Lagrangian and Eulerian framework, where in the Lagrangian in the framework we follow individual particles of the fluid as they move over the time. It's often used in a it's often used in simulations of specific particular objects. Eulerian, here fluid properties are tackled at fixed point in space. So this is commonly used in most CFD simulation, especially when the flow is steady or when we need to study the flow at specific location. Okay, so this is conservative form like rho, rho u, rho v, rho w, rho t. This is a conservative form, conserved form, and in the independent variable, independent values u, v, w, p. This we call as a primitive form. So this is generally used for the compressible flow as the density is changing always, and here this is for incompressible flow because it is not having combination of two parameters with the one parameter with the density, right? So this is a primitive form which is for applied generally used for the incompressible flow, and this is conserved form where there is a always change in the property, that is density, and having combination with the other properties. Then we always talk about the grid structure, structured grid. So these grids, whether it is regular or organized layout, having organized layout, they are computationally easier to work with, but they may not work well for complex domain. So unstructured grid having more flexible can be used to model complex geometry, but they are computationally more demanding. So because whatever the shapes we are having, suppose aerofoil shapes we are getting, then in that there is always it is not possible to having the structured case always. So there is always unstructured mesh, maybe having the triangular mesh at this location and having square or quad element at this location and pi element at the corner of borders of the section, border of the geometry. So block structures, again, these are used often when different regions of the domain require different grid structure. The blocks are structured, but each region can have its own grid configuration. Again, there is an overset grid. This grid overlap and are used when the geometry changes, such as in moving bodies, right? So interpolation is used to connect the different grids in this particular case. Now there are various variable storage techniques. What are the calculations we are calculating? What are the data or what are the values for the parameter we are calculating? Like suppose cell centered variable storage methods, like variable storage means variable means suppose I am having this particular try element. Okay, one more here, one more here, and one more suppose here. So with this cell centered method, first is suppose I am having cell centered. Here we can say this is the value where we are storing the variable values. Okay, and vertex centered means we are calculating the variable storage values at these vertices. Okay, at the points, at these points. Others are co-located and staggered away. Now choice method. So understanding these methods allows us to choose the most appropriate approach depending on the problem we are trying to solve. So in the coming lectures, we will discuss about the in-depth understanding of finite difference method and finite volume. Okay, thank you.